Welcome to Lecture 12.3, Integrals Involving Exponential and Logarithmic Functions. Let's first do a little bit of review about exponentials. Remember that if we take the derivative of the natural of Euler's constant with the natural exponential, Euler's constant raised to the x, or e to the x, this equals e to the x. This is one of those weird places in nature where the slope of a function is actually equal to the functional value at every point. So by nature, the integral, which is the antiderivative of e to the x, is also going to equal e to the x plus c. If we replace the exponent with a function of x, remember that's what u stands for, some function of x, and we'll look at an example in a minute so you know exactly what I'm talking about. This is now an example of the chain rule. So we take the derivative of the outer function, e to the u, which is simply e to the u, times the derivative of the inner function. Well, the inner function is the actual exponent itself, so we take the derivative of the exponent, notated by u prime here. So the derivative of e to the u, or e to a compound function, e to a function of x, is equal to u prime eu, where u is the exponential function. So again, by rule that integrals are antiderivatives, if I take the antiderivative of u prime e to the u, then I'm going to get e to the u plus c. Okay. So here's an example. Here, notice instead of x in the exponent, I have 3x squared. So here, the example is that u would equal 3x squared. When I'm taking the derivative of e to a function of x, again, take the derivative of the outer, which is e to the u, which is just this e. I actually literally repeated in the answer, e to the 3x squared. It doesn't get touched. And then I multiply it by the derivative of the exponent, which is 6x. And so this is my answer. So my integral of 6x e to the 3x squared, by rule, by being an antiderivative, or the inverse function of a derivative, we're going to get e to the 3x squared plus c. Okay? So pragmatically what this means is when you're looking at a integral, and if you have an integral with an exponential composite function, that means e to the exponent is a function of x, it's not just x, and the derivative is also part of the integrand. The derivative of the exponent is also in the integrand. Then we can use similar substitutions as we did in section 12.2 for the power chain rule. Let's look at how we do that. So notice if we have this original integral where there's e to the u and there's also the derivative of the exponent, dx, we can rewrite this doing substitutions, e to the u du, and this is the same as e to the x dx, which the integral of e to the u with respect to u is just simply e to the u plus c. So let's see how that works. I'm going to call this method the EGIC method. I prime, G, I, C, and I pronounce it EGIC. Okay? Hopefully it's something it's easy for you to remember. The first step is to find the inner. We did this again in 12.2. We followed a similar process. For exponentials, for integrals with e to a power, this is always the exponent on e. So here are u, our inner function, u equals x squared plus 2. That should read 2x, okay? Sorry, this is a typo here. It should be x squared plus 2x. I did not see that till just now, okay? Our second step is to find I prime, or the derivative of the inner function. This is simple. Just take the derivative of what we identified in step 1. So du, technically it's du over dx equals 2x plus 2. Remember, this is a 2x here, so this is where it might be confusing to you. Okay? If I think of this du dx, which is the derivative of u with respect to x, as a fraction and multiply both sides by dx, then I get this model here. And the reason we do that is because it makes it easier for us to see the substitution. Okay? And you'll see that in a minute. I notice up here that I don't have 2x plus 2. But if I factor out the 2, I see a part that I do have, which is x plus 1. The third step I call Go Fish. And all I'm talking about here, and I'm sorry if you're not American and you don't understand this reference, Go Fish is a children's game where you ask someone if they have cards that match what's on your hand, and if you do, you take them. Okay? If not, you go fish and look for something else and add something else. Okay? So this step is really just about matching and substituting the parts of u and du into the original integral. We're starting here. We're going to use these parts because we were trying to build this, the integral of e to the u du. Because as soon as we have this, we know that the answer is simply e to the u. All right, so we're going to play Go Fish. The way we do that, we say, okay, is there any x squared plus 2x's? Yeah, they're what's on the exponent, right? So notice here, I put the original equation, and I put the u, which is in yellow here, okay? Then I go to my du. Got any dx's? Here you do. I made it blue. Got any x plus 1's? Yes, we do. I made it blue. Got any 2's? Uh-oh, we have a problem. There aren't any 2's. But remember, if we have a constant, we can add a constant into the integral equation, as long as we add the reciprocal of that constant out front, because 1/2 times 2 is 1, and therefore we haven't changed the value. 1 times anything is the same value. So we haven't changed the value of the equation. Okay? So notice now we have all of the parts. X plus 1, dx, and 2 is all du, so all these pieces go away and become du, the blue piece and that red 2. And we're left with the integral of e to the u because this yellow part is u. So I get 1/2 e to the u du by just substituting in du for the blue parts and the red 2 and u for the yellow exponent. Well, as soon as I'm there, I'm ready to solve because the answer to this is simply e to the u, and that's our last step, is to integrate. So I get 1/2 e to the u plus c, and all I have to do is now reverse substitute. Since u equals x squared plus 2x, I just plug it back in there. And we're done. So now it's your turn. Oh, I'm sorry. The c on eGic is to check. We check our answer by taking the derivative of this. When I take the derivative of this, notice I get the exact answer that's in the integrand. This is very important for you to do on the test because you don't want to make some kind of mathematical mistake like I did here by dropping the x. If you didn't pay attention to that, you would have thought the derivative was just 2x, and we would have got really messed up. Okay? So you want to take the derivative of your answer and make sure you get back to where you started. So here again, I have some of the rules about the power rule. Let's go ahead and do 3 problems. This is a good time for you to hit pause and try each of these 3 on your own following the eGic method. As soon as you've done a problem, hit play again, and then we'll get started and you can see how you did. Okay, so notice this first one, there isn't a power on x, it's just x. Excuse me, there's a power on e, but it's not a function of x, so it's not this model, it's just e to the x. Okay, so all I have to do is pull the constant out in front, which I'm allowed to do, and I have the integral of e to the x dx. Well, that's a simple answer, it's just e to the x times the 5, so my answer is 5e to the x plus c. So this is probably the simplest exponential integral to do. Notice the other two, u is a function of x. It's no longer just x, it could be anything. It could be x plus 2, 2x, 4x, etc. As soon as there's a u here, I need to use the eGic model. When it's just e to the x, I don't need this model. I just do a direct integration. When there is a function that I can think of as u, then I do the eGic model. Remember, the first step is u is equal to the exponent, in this case x squared. Then I take the derivative, the second step, inner prime. The derivative is just the derivative of the u that we just looked at, so I get 2x dx. Now I do substitution. Notice that I have all of the parts here. 2x dx goes away when I replace it with du, and I'm left with e to the u. And we know that the integral of e to the u du is simply e to the u plus c, and then I just plug back in my u value, which is x squared. I've done another one. Let's look at one that's a little more complicated. Here I set u equal to negative x cubed. Now why did I set it equal to negative x cubed? Because it's in the denominator, and I want to think about this as a fraction in the numerator, that this piece is no longer in the denominator but the numerator. Since it's in the denominator, I put a negative on it. Okay. Typically what we would have done, like we did for derivatives, we would have rewritten this first, and I think that's a really good idea to do here, and I wish I had have done it in these slides. So if u is equal to negative x cubed, then du equals negative 3x squared, right? Negative 3x1, the exponent 1 less dx. So now I play my matching game. Do you got any negative x cubes? Yes, that's on the e. Okay. Got any dx's, yes, got any x squareds, but notice what I'm missing is the -3. I add that inside the integral and offset it by its reciprocal. Once I've done this, I can do the substitution. I have e to the u du times -1/3 of that integral, which of course is just -1/3 e to the u plus c. I plug my values back in, so I get -1/3 e to the u, which was -x cubed plus c. Notice a negative exponent means it's in the denominator, so I can move it to the denominator with the 3, which is already there. Either of these answers would be fine for the test, but it's always a good idea to put it back in the original form. Okay, so we've done exponentials. Now let's look at natural logs. Remember that the derivative of a natural log is 1 over the argument, or specifically 1 over x. Okay, so the integral of 1 over x dx is simply the natural log of x plus c. If the argument of a natural log is again a function of x, then it's a chain rule. So we take the derivative of the outer, which is 1 over the argument, 1 over u, times the derivative of the inner, which is simply the argument, which is u prime, or du. So I get, u prime over u. So of course, if I'm taking the integral of u prime over u, then I'm going to get the natural log of u plus c. Again, we're just going the opposite direction. Let's look at an example. So the derivative of the natural log of 3x squared is first the derivative of the outer. The derivative of any natural log is 1 over the argument. So I get 1 over 3x squared. 1 over 3x squared. The 3x squared is in the denominator. Times the derivative of this argument. The derivative of 3x squared is 6x. So I get 6x over 3x squared. So notice here I have the integral of 6x over 3x squared dx is going to go back and be the natural log of 3x squared plus c. So notice here, if we are taking the integral of a quotient, so you're looking at a new problem and you're not sure which one it is. You're taking the integral and it happens to be a fraction. And if there's no power on the denominator, now let me explain what I mean by this, because there is a power there, right? There's not a power on the entire denominator. What that means is there would be a parenthesis around the entire denominator and an exponent outside the parenthesis. There can certainly be powers in here like we see here to use the natural log. Okay? When I say there's no power on the denominator, I mean on the entire denominator, parentheses with an exponent outside. And the numerator is the derivative of the denominator. So if I see I have a fraction, there's no parentheses and power outside it in the denominator, and the numerator is the derivative of the denominator, so I have a u down here and the derivative up top, derivative over the function, then I know that this is a natural log composite function, and we can use similar substitutions as we just did with the exponentials. Okay, so if I have u prime over u dx, I can do the substitution and write this as 1 over u du, which is the same as 1 over x dx, which of course is the natural log of u plus c. So now let's look at this example. We're going to follow the exact same model, EGIC, whatever. For quotients, the u, the inner function, will always be the denominator. Okay, and if this was a fraction with a power in the denominator, we would still follow the first part of EGIC the same way. It just would not be a natural log. It would be a simple power rule with a negative exponent. Okay, so we've set up u. It's always the denominator. When we have a fraction, the u is the denominator. We take the derivative of u from the first step. So the derivative of this is 2x plus 4. Again, I see that that doesn't match exactly, so I factor it. Now I get 2 times x plus 2, which I see there, dx. The next step is go fish. Same with u and du. So I'm going to look here. Do you have any x squared plus 4x plus 3's? Yep, it's in the denominator. Got any dx's? Yep, it's right there. Got any x plus 2's? Yep, it's right there. And so I've highlighted those all here. The du's are in blue. The u's are in yellow. And notice once again, I'm missing the 2. I'm allowed to add a number. I'm not allowed to add an x or any variable outside. I can add a number inside as long as I offset by its reciprocal outside, which I've done here again. Okay, when I do the substitution now, substituting in du for x plus 2 dx times 2, I get that there. And then, of course, u is in the denominator, so I get 1 over u. So here's my problem. Again, the integral of 1 over u du is simply the natural log of u. So that's my next to my last step is to integrate 1/2 natural log of u. The constant stays and is in the final answer, plus c, and then I substitute the u back in. The last step is to take the derivative of this and make sure you get back to here. I'm going to let you do that one on your own. Oops. All right, let's look at a couple examples here. Let's hope this works this time. Again, you have the same rule, EGIC right here, and kind of a little reminder, if you have the integral of 1 over u du, or the integral of u prime over u dx, then we can use the natural log. So what happens again is notice these are both quotients. That's the first clue for you. If you have a quotient, then look to the denominator. Set u, the inner function, equal to the denominator, take the derivative, and see if the pieces are there. In this first one, they are. So again, I'm going to do the substitution. U is in the denominator, so it's 1 over u, and du, 4dx, notice is in the denominator or off to the side. So here I simply have the natural log of u. This is my setup, 1 over u du. The integral is the natural log of u, plus c, don't forget your plus c. And then I plug back in the value of u. Next one's just a little more complicated. Again, I have a quotient, so I set my denominator equal to u. I take the derivative, du, 2x minus 6dx. I see that doesn't match, so I factor it. I get 2 times x minus 3, and now this 2 is what's missing. You can see it. I've added it in there. I've offset with 1/2. Believe me, I'm sorry that I kept using 2. I'm surprised that every example uses 2 and 1/2. They're not always going to be that way, and I know you like different examples. So now I can do my substitution, and again I get 1/2 1 over u du, which is 1/2 times the natural log of u, and I substitute in the natural log of u plus c. Okay? We just have one more problem here. I wanted to give at least one word problem so you would see what's going on here and how to do one of these. Suppose the rate of change of the value of a house that cost $200,000 in 2015 can be modeled by dv dt. The rate of change, or the derivative of v with respect to t, equals 15.4 e to the 0.077t, where v is the market value of the home in thousands of dollars, and t is the time in years since 2015. So notice our two questions. One is to find the function that expresses the value of t in terms of t. All that's saying is give us the original function for the market value of the home, v of t. Okay. Well, if we have the derivative, we know that the way that we find the original function is to take the integral. Okay? We know that this is true for any function. The original function equals the integral of the derivative. Okay? So all we're going to do here is take the integral of dv dt, which is 15.4 e to the 0.077t. Now remember your EGIC model. Remember our inner function, is always the exponential function. Okay? So, I don't even show any of that. So our u is equal to 0.077t. Our du is 0.077. Okay? Since I don't have a 0.077 in this original formula, I've got to add it, and remember when I add it, I have to multiply by its reciprocal. Now the other problems I showed you, I put it on the outside, and you can certainly do that. So on the outside, you'd have 15.4 over 0.077. Now I'm ready to do the substitution. Well, now I'm ready to do the substitution. This is e to the u du. E to the u du, which gives me e to the u plus c. Okay, so I multiply by this constant, e to the u, same u, plus c. All right. Now remember, if we're ever we really want this functional value, we have to have a reference point for c. This is not the answer to part A, okay, because we don't know what this constant is, so we have to figure it out. In a problem, it will give you that reference point. Notice it says the value of the house was $200,000 in 2015. 2015 is our 0 marker, since t is the number of years since then. So in 0 was 2015. So when t equals 0, the value, or v, equals 2,000 or 200,000. Remember, this is in thousands, so we just write it as 200. So I plug this in. 200 equals 200 e to the 0.007 times 0. Well, remember, that makes that e to the 0. Anything to the 0 power is 1. So I get 200, that's the value of the house, 200,000 equals 200 plus c. So in this example, c equals 0. So our answer to A actually is just 200 e to the 0.077 t. Part B is very simple to find. Find the predicted value in 2025. This is after 10 years, so t is going to equal 10. I plug that in and I get 431.95. Now be careful again. Remember that V is expressed in thousands of dollars. So $431,000 or $431,950. Make sure you answer correctly to the units, etc. Okay? So a couple things here. Remember that you have to figure out what the value for C is. If the problem does not give you a reference point, like it's telling you here that the functional value is 200,000 when t is 0 or time is 2015, what that means is there's a common sense answer for the reference point. You'll typically see that around 0. So for example, a common one is revenue. The revenue at 0, if revenue is the money you make from selling a product or a service. So if you sell 0 products, you're going to make 0 money. So in revenue functions, it's usually R of 0 equals 0. Okay. Remember that fixed costs are the costs you have if you don't make anything. So that's C of 0, and these are not usually 0. Like the fixed cost might be a couple $1,000s because you're still paying rent or utilities even if you're not making anything. Okay, so again, when you're trying to find a functional value or these word problems, you've got to figure out what the value of C is. And you either need a reference point, like given in this problem, or if there is not one, you have to figure it out. And it's a simple answer, and it uses common sense. Okay, so think about it and don't overthink it.